we're going to look at a few other things that affect how molecules interact. First thing we're going to look at is electronegativity. So this is another pattern that we can see in the periodic table that shows us how much an atom attracts electrons. So this pattern is the opposite of our ionization energy. So electronegativity, it increases left to right across the periodic table, increases from bottom to top. So the most electronegative atom here is fluorine. The least is francium. So fluorine really wants electrons. Francium, not so much. So what that means is that if francium is trying to share electrons, it's not going to really care. It's not going to want the electrons that much. Whereas fluorine here, it's going to pull on electrons very hard. That's going to result in something called polarity. So polarity is based on electronegativity difference. So if we have two atoms that have a high electronegativity difference, they are going to share electrons unequally. So if there's zero or very low difference, the electrons are going to be shared pretty equally between two atoms. So an example of that would be if we have hydrogen bonding with hydrogen. It's got the same electronegativity, it's the same atom, so there's no overall direction that the electrons are being pulled. So this is a nonpolar covalent bond. There's equal sharing. A polar covalent bond, there's a higher difference, and the electrons are shared unequally. So for example, if I have a bond between hydrogen and oxygen, oxygen has a much higher electronegativity, so it's going to pull on these electrons a little bit. And that's going to make it so that the hydrogen here ends up slightly positive. So that's what this little squiggle means, is slightly, or partial. So partial positive charge. And this is going to have a partial negative charge. These are not actually ions. What it just means is that it's sharing, but it's like sharing between two siblings that don't get along very well, where one of them is going to try and, borrow it a little bit more than the other. So oxygen's kind of bullying that hydrogen and pulling the electrons toward it. This polar bond is also called a dipole, and it's going to affect how the molecule behaves. So we'll take another look at the bond polarity. So here's an example with chlorine. Chlorine's bound to chlorine. It's nonpolar covalent bond, very equal sharing. Hydrogen and chlorine, polar covalent. So there's an unequal sharing, but notice they're still sharing. These electrons are still shared between the two atoms. Ionic bond is essentially an extreme version of this, where the sharing has gotten so unfair that one of the atoms has actually taken the electron from the other one. So chlorine here has taken the electron from sodium, so it formed a sodium ion and a chloride ion. The polarity here is going to affect the shape. So we're going to look at shape and polarity together to look at how it actually affects how a molecule behaves and what it looks like. If you are in a lab, you'll also be working on that in the lab. If you are wanting to look up additional information about this topic, it's based on VSEPR theory. That's called valence shell electron pair repulsion. And it's really just based on the idea that if you have two negative things, so if you have two things that have a negative charge, they're going to push away from each other. So first we're going to take a look at shapes. This is a summary of the types of shapes that we'll be looking at. There are more shapes that you can find in different sources, but we're going to focus on some basic shapes. The number of electron pairs here is essentially the number of electron groupings around an atom. So this could be a number of single bonds, it could be double bonds, it could be triple bonds. It doesn't matter how many of them. We'll take a look at some examples. The electron pair geometry, 0 lone pairs, so we're looking at the center atom. So this center atom has 0 electron pairs that are to itself, and there's 2 things that are bound to it. That's what this 2 means. 2 things to bound, and there's no lone pairs. For 3 here, we have 3 things attached and no lone pairs. Or we have 3 things attached. Notice we can have 2 atoms and a lone pair, or we can have 3 atoms for these 2 structures. 4 groupings, so 4 atoms attached, or 3 atoms and a lone pair, or 2 atoms and 2 lone pairs. So there's a variety of different combinations. Each of these is going to result in a different shape. So this structure here is going to be linear. This one with 3 atoms attached and no lone pairs, trigonal planar. Make sure you distinguish planar from pyramidal. We'll look at that in just a moment. There's bent or angular if you have 2 attached and a lone pair. Tetrahedral, which we'll look a little bit at how that works 3-dimensionally. Trigonal pyramid, and bent or angular. So you want to be able to distinguish these shapes. There's just some examples. We'll start with the 2 attached. So this is a linear molecule. Notice there's 2 things attached and there's no lone pairs. So this creates a linear shape. Trigonal planar. This is, we have 3 groups. Notice it doesn't matter that this is a very different group or that this is a double bond. That there's 3 different areas where there's electrons around that atom. So this is a trigonal planar. This is another 3 group. We have 2 attached and a lone pair. So there's 1, 2, 3 groups. Tetrahedral, so this is a 4 group. So there's no lone pairs on this carbon. We have 1, 2, 3, 4. It's another 4 group. We have 1, 2, 3 bonded things, and then we have a lone pair, so 4. 1, 2, 3, 4. And this gives us a trigonal pyramidal shape. So notice that because of this 3-dimensional shape, that we get like a little tripod effect. Notice that all of these are kind of going down. So it doesn't look like there's anything up here because we have those electrons that are pushing everything else away from it. Here's another 4 group. This has 2 lone pairs. You have 1, 2 bonded, and 2 lone pairs. 1, 2, 3, 4 groups. This gives us a bent shape. Sometimes you'll also see it listed as angular. You'll combine these shapes with polarity to look at polarity of molecules. So if you have a lab, you'll do this in lab. If you're not, then you'll work on it in other ways. For a nonpolar molecule, there's no difference across the molecule. So if we look back at our tetrahedral here, these atoms are all the same. So there's going to be no overall pull across this molecule. So even if these bonds were polar, this wouldn't be a polar molecule because all of these bonds are going to cancel each other out. Kind of like a perfectly balanced tug of war. Whereas if I look at this molecule, if I write it like this, if I have oxygen, so it's bent, this oxygen is going to pull on those electrons. You can see when I draw it like this, that the electrons are being generally pulled up. So the electrons are overall being pulled in this direction. So that makes it a polar molecule. So there's an overall pull or directionality to the electrons.